Now let us talk about momentum, okay, which is part of of topic 5. So further momentum, and it's called further because we go beyond the one-dimensional collisions that we talk about in unit 1 at the AS level. So I'm gonna kick this off by directly defining what momentum is. So momentum is expressed with the letter P, lowercase p, equals to mass times velocity. And for the time being, maybe I'm gonna drop it in the next videos, but for now, let's put these little hats on top of the letter P and V to denote that these are vector quantities. So momentum is a vector quantity with units kilogram times meter per second. It doesn't have a special name, it's just kilograms times meters per second. Why the letter P? For those of you who are curious about history, it's from P because in Latin it comes from the Latin impedus, which means something that moves, I think, or something like that. So there's the letter P there, okay? Because, for example, for force, you just use F. Anyway, this is irrelevant to your studies. Let's go see something about these units. So since P is measured in kilograms times meters per second, notice that we can write this as kilograms times meters over seconds squared. And since I introduced seconds squared in the denominator, I have to multiply by seconds in the numerator to cancel the seconds in the denominator. But now notice that this is simply 1 Newton. So this is Newtons times seconds, okay? So momentum is also measured in Newtons times seconds, okay? So that's another unit for momentum. And since momentum is a vector quantity, so because momentum, oops, I warn you about my handwriting. So anyway, so since because momentum is a vector quantity, it can be resolved into an x and a y component. Okay, so let's see this example. So if we have our y-axis and our x-axis, okay, and this is our momentum vector p. In this example, let's say that we know the angle theta between the vector and the horizontal. Then we can resolve this into an x component. So this is the x component. Px is simply p, the magnitude of p, okay, times cosine theta. And you can put little arrows here to denote the components, okay? And this is the y component. Py is p sine theta, all right? But in other problems, they might give you, this is still the y-axis, this is the x-axis, okay? And this is the exact same vector as we saw here, okay, in the previous example. But let's say now they give you phi, the angle that the vector makes with the vertical. So we can keep our cool and analyze into the x component, which is now px equal to p, the magnitude of the momentum, times sine phi, right? And the y component py is simply p cosine phi. And a rule I use to remember which is the cosine and which is the sine is that if my component, so this component, touches the phi angle, then that's the cosine phi component, okay? And again here, this component, the x component, touches, so I'm here now, okay? So this component touches the theta angle, so that's my cosine theta, all right? Whereas this component, if we come back to this example, okay, this component does not touch the phi angle, so it's sine, okay? Same here. This component does not touch the theta angle, so that's our sine, okay? Let's delete that, we don't need it. And let's move on, okay? So since we are gonna be dealing with two-dimensional momentum, we will need to analyze the momentum into its x and its y component. And there is one more trick that you need to know that I will mention later. But for now, let's go and examine how momentum is related to Newton's second law. So momentum and Newton's second law. So recall that Newton's second law is force equal to mass times acceleration. And again, I'm using those hats to denote vector quantities. And again, I will probably drop it at some point or forget about it. So, but for now, let us use arrows. So what is acceleration? Is the change in velocity with respect to time, right? And we can use the delta notation, but we can also use the d notation, okay? So dv over dt, all right? Actually, this is not needed here. Let's, no, let's keep it, it's fine. So let's go back to this, okay? And see what we can do. So since mass is a constant, we can drag it and put it into this delta, okay? So this is delta mv over delta t. So since it, when we take derivatives, all right, the derivative of a constant is 0, right? But if we take the derivative of a constant times a variable, all right, then the constant can be taken out of the derivative. So here I take it in, so I can take it in for free. But now notice that this quantity over here is momentum, right? So this is delta P over delta T, okay? This is a significant result because this is how Newton actually defined his second law. So in words, and you might be asked, so let's write this down. So the rate of change of momentum, of momentum of an object. And what is this rate of change of momentum? Is delta P over delta T. So you take the rate of change of momentum of an object is proportional to the applied force, okay, and it is in the same direction, okay? So this is an alternative expression for Newton's second law. And I'm gonna write down this optional part, so you can skip the video if you don't want to hear about this because it's not part of your spec, but I just want to show you something. So since force is dp over dt, and since I can write this as d over dt of mass times v, right? Then using the chain law, notice that this is nothing but mass times dv over dt, which is your familiar form of the Newton's second law. But then we can also do a second term, v times dm over dt. So we usually assume that dm over dt is 0. Okay, so for example, if we are dealing with a car, the car mass doesn't change by a lot, though it does change, right? The car has car weight is about, say, 1 ton, right? But it has maybe 50 kilograms of gasoline. So as the gasoline is burning, the mass of the car reduces, but it's really a very small effect compared to the mass of the car. But if you're dealing with rockets, dm over dt is actually not 0, right? Because this is how a rocket moves, by burning fuel, right? So this is something to think about, okay? It's not part of your spec, but it's good to know. So I'm gonna write this down. So for rockets, dm over dt is not necessarily 0, all right? And the same goes for if I am in a very small boat in a pond, right? And I don't know, I have something in the boat that I don't like and I throw into the pond, maybe a rock, maybe a large rock, then my boat is gonna move. Why? Because, okay, you have a change in momentum because the rock is a very large body, etc. But in some sense, the mass of the boat is also changing. So anyway, that's something interesting, I thought. So you can skip it. You don't need to know about it. It's not asked. So I'm gonna move on. Now let's go talk about momentum conservation, okay, which is part of your spec. So momentum conservation. So since F is delta P over delta T, then if F is 0, sometimes you see it as sigma F, so the sum of all forces, okay? So maybe it's better to write sigma F there, but it's okay. I hope you guys are following. So if the sum of all forces acting on a body is 0, okay, which means i.e. there is no external force, comma, then delta P over delta T is 0, therefore delta P is 0, okay? And in going from here to here, we assume that delta T is not 0, okay? So, but what is delta P? If delta P is 0, this means, which means that P final minus P initial is 0, or P final is equal to P initial, okay? So in long writing problems, they might ask you, what are the conditions to have momentum conservation? So you will have to write that if in the absence of an external force, or if the external forces are 0, or if the total, the sum of external forces, etc. is 0, then momentum is conserved. But why is it conserved? Because of this. You can derive this mathematically, okay? So, by the way, the notation delta means change between some final condition and some initial condition, okay? Whereas D, this notation for momentum that we saw a little bit earlier, D, means an infinitesimally small change. So this is this goes back to, for those of you who are heavy into math. So if you have a function like this, for example, delta would be, if this is f of x and this is x, and this is say x final, and this is x initial, then delta f will be f at x f minus f at xi, whereas df involves an infinitesimally small change. So df will be this. Okay, so this will be df. We don't need this there. Okay, so big change delta f, small change df. All right, so, and I'm a physicist, so mathematicians will flip if they see this, but I'm just giving you a rough idea. Okay, now let me remind you of what you saw in your AS level physics. So in unit 1 AS physics, you only saw conservation of momentum in one dimension. You dealt with 1D collisions. Okay, so as an example, let's say that you have some mass 1 that travels with velocity v1, okay, and collides with some, maybe these are bigger balls or something like that, and you have another mass m2, and its velocity is 0, so it's stationary. So I like to divide the space into the before and after. Okay, so before we have maybe cue ball hitting an object ball which is stationary. Okay, but at the AS level, then you saw examples in which mass 1 keeps moving to the right with some velocity v1 prime. It can also move to the back, by the way, as far as it's in the same line. So when we say one-dimensional, we mean that everything lies along this line, okay? And then mass 2, the object ball, moves also to the right with some velocity m2, and then you have v2 prime. So the conservation of momentum still applies. So for the before condition, we have, what are the momenta? We have m1 v1 plus 0. What do we have afterwards? We have m1 v1 prime, which is the momentum of the first ball, plus m2 v2 prime, which is the momentum of the second ball. Okay, and if we combine these, we find m1 v1 must be equal to m1 v1 prime plus m2 v2 prime. Okay, or other examples, maybe this ball m1 will bounce off and move to the left, for example. Okay, maybe it moves this way, but the object ball moves to the right, so that's still valid. And if the first ball moves to the left, we will have to include a minus sign, but that's a different example. So let's keep it simple. Let me also do one more example from unit 1, and then we will do two-dimensional examples. So the explosion example. So explosion example. During an explosion, what we actually have is a very curious situation. So before, let's say that we have something that explodes, okay? It has a mass m, capital M, and a velocity is 0 actually, okay? So the total momentum before is actually 0, okay? And let's say that this explodes, okay? And let's assume that it breaks into two masses. So it breaks into a mass m1 with velocity v1 prime to the left, and another mass m2 with velocity v2 prime to the right. So the momentum after, the total momentum after, which has to be conserved, is equal to minus m1, sorry, I meant to use red color. So let's do red. Minus m1 v1 prime minus, plus m2 v2 prime. Okay, so the conservation of momentum in this scenario gives us that 0 is minus m1 v1 prime plus m2 v2 prime, which means that in order for this to happen, the fragments have to move in opposite directions, actually. Otherwise, momentum is not conserved. So you cannot have an explosion in which everything moves in one direction, okay? That will violate momentum, okay? Momentum conservation, I'm sorry. So m1 v1 prime plus m2 v2 prime, all right? And we get a bonus equation in this scenario, which tells you that the total mass before must be the same as the two masses afterwards, okay? So this is AS level one-dimensional collisions. Now let's go see two-dimensional collisions. So let's advance to A level 2D collisions. So a possible scenario might be the following. So again, I divide my space into a before the collision and an after the collision space, okay? So let's say I have, maybe it's the same cue ball as before, some object that has mass m1 and travels with velocity v1 to the right, okay? It collides with some mass m2, which is stationary, okay? So that's the situation before, but after we get the following, okay? The first ball moves in this direction, okay, with that makes an angle theta with the horizontal, and the second ball makes an angle phi with the horizontal, and it moves in this direction, so has a mass m2 and velocity v2 prime. So what I like to do is to analyze the momentum vector into its x and its y component, and in 2D collisions we basically have conservation of momentum in both axes, both x and y. So what's the x component of the momentum before? It's just m1 v1, because only this object has momentum and it happens to be in the x direction, okay? And this object has no momentum, all right? And in the y direction, the total momentum is actually 0, okay? There is nothing moving in this direction. Now, let's go see what happens with the momentum afterwards. In the x direction, okay, we have components from, both this mass and this mass, right? So what is the x component of the momentum for mass m1? It's gonna be m1 v1 prime cosine theta, because this component of the momentum touches this angle theta, as we just said earlier, okay? And if we analyze the x component of the mass 2, okay, we get another term plus, because both move to the right, okay, plus m2 v2 prime cosine phi. I know it's terrifying, but this is how this is what it looks like. Now, in the y direction, we have object 1 with mass 1 traveling north, and object 2, actually it's north east, but in terms of the y-axis, I'm trying to say that if we draw a y-axis like that and we find the y component of mass 1, that's gonna be m1 v1 prime sine theta, okay? And then the y component of mass 2 is gonna be moving down, so in the negative direction, so it's gonna be minus m2 v2 prime, and then sine phi, okay? So the y component of mass 1 moves up, and the y component of the momentum of mass 2 travels south. So it comes with a negative sign. All right, so as I promised you then apply conservation of momentum in the x direction and in the y direction independently. So for the x-axis, you have mass 1 v1 is equal to m1 v1 prime cosine theta plus m2 v2 prime cosine phi. And in the y direction, you have 0 before, right? Equal to m1 v1 prime sine theta minus m2 v2 prime sine phi. And this is sort of a generic example of momentum conservation in 2D, okay? It might be anything else. Maybe they give you this angle with respect to the vertical or some other scenario. But the general idea is that you divide your space to a before and an after space. You find what's going on in the x-axis before and what's going on in the y-axis before, and then the same for after. And then you set the x component of the momentum before equal to the x component of the momentum after, and the same for the y component, okay? So this is the algebraic way. So I'm going to write this down. So this is the algebraic way. This is the algebraic way of working with momentum conservation. There is a second way that is frequently asked at the A level, and it's called the vector way. So the vector way of analyzing momentum conservation. And if they ask you questions like this, they usually mean that you have to use a ruler to measure the length of your momentum vector and convert it into the units they ask you to. So for example, you can say that 1 centimeter is 10 kilograms times meters per second, or something like that. So you need to use a ruler to calibrate your vector. So what I'm trying to say is that maybe momentum is 10 kilograms meters per second. So you're going to do something like this. You're going to say that this square is 1 kilogram meters per second. So for your vector, you will need 10 squares. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this will be P equal to 10 kilograms meters per second. Okay, so 1 square corresponds to 1 kilogram times meters per second. All right, and then you also need to use a protractor for possible angles that they give you. Okay, so you have to measure the angles as well. So let's go see the vector way. So will I need extra space? So let's examine the exact same thing we just saw. So before, we have a ball M1 moving to the right with velocity v1, and it hits a ball that is stationary. Okay, and after we have the two balls moving, making an angle theta with the horizontal for mass 1. So mass 1 v1 prime and mass 2 v2 prime makes an angle phi with the horizontal. So vector wise, what's actually going on here is the following. So remember that actually we have pi must be equal to pf, or the sum of all vectors before must be equal to the vector sum of all momenta after. So how are we going to do this? So let's draw this easy part. So P1 is M1 V1. All right, so this is the vector representing the initial momentum. Okay, but afterwards we have this guy, which is P1 prime, say. Okay, I mean, this guy is P1 prime and this guy is P2 prime. So how do we make this vector equal to this? You simply, you can picture, you can take this vector, okay, and parallel transport it to the tail of P1. So this is going to be your P2 prime. P2 prime is M2 V2 prime, okay? And then how, so the sum of momenta after has to be equal to the sum of momenta before, all right? So the only way to close this triangle is to parallel transport this initial vector, okay, for mass 1. You kind of parallel transport it, imagine like taking this vector and parallel transporting it here, okay? So this is going to be P1 prime equal to M1 V1 prime. So that's a V, I'm sorry. So this now, let me use black. So this angle is gonna be phi, right? Because this is the angle this vector P2 prime makes with respect to the horizontal that happens to be the direction of P1. So that's phi. And then if that's phi, this is theta. Is this the only way to do it? No. You can also draw your initial vector P1. So P1 is the same. P1, in both cases, I mean, it's the same, times V1. And then you can parallel transport P1 prime and put it here, okay? So this is P1 prime equal to M1 V1 prime. And now this angle must be theta, right? And to close this triangle, because P1 is the sum of all the momenta after. So if you sum P1 prime and P2 prime, you should get P1. So this is going to be P2 prime, which is equal to M2 V2 prime. And this angle is now phi, okay? So this is the vector sum. The sum of the momenta before should be this equal to the sum of the momenta after. Now let's go see what happens with the kinetic energy. So conservation of kinetic energy only occurs, and I capitalize that, okay, only occurs in elastic collisions. Collisions. So in the same situation as before, so let's say that this is our situation before and this is our situation after. And this is going to be a crazy scenario in which you have a mass 1 moving with velocity v1 to the right and a mass 2 moving with velocity v2. So maybe this is a bullet and this is a moving target moving this way, and they somehow hit each other, okay? So this is the situation before, and the situation after is like this. So you have M1 v1 prime, and then you have maybe m2 v2 prime. I drew it this way on purpose because the kinetic energy before is 1/2 m1 v1 prime, m1 v1 squared plus 1/2 m2 v2 squared, and the kinetic energy after is 1/2 m1 v1 prime squared plus 1/2 m2 v2 prime squared. Okay, so if we have kinetic energy conservation, this means that we have an elastic collision, and if 1/2 m1 v1 squared plus 1/2 m2 v2 squared is equal to 1/2 m1 v1 prime squared plus 1/2 m2 v2 prime squared, then the collision is elastic. So I drew this momenta this way because some students occasionally get confused and they think that, for example, they should analyze this velocity into its x and its y component, etc. No, all you need when you deal with kinetic energy is the magnitude of the velocity and nothing else, okay? Because the kinetic energy is a scalar quantity, so you don't need to use components of velocities or any sort of thing like that, okay? So please be careful when you deal with kinetic energy. So I'm gonna write this down, so careful. If in dealing with kinetic energy, only the magnitude of the velocity must be used. So no vector resolution shenanigans whatsoever. So one last thing that will come handy in relationship with momentum and kinetic energy, so is the following. This is something that might be needed in momentum conservation problems, but also later in subatomic physics and stuff like that. So kinetic energy's relationship with momentum. And I'm gonna put it in parentheses here that it's useful when dealing with particles. So useful when dealing with particles. So the kinetic energy is 1/2 mv squared. This is what we usually use. We can also write it as 1/2 m squared v squared over m, right? If I delete the square and the mass in the denominator, I get back 1/2 mv squared. But now notice that what I got is 1/2 mv squared over m, but this is nothing but p, so this is equal to p squared over 2m. So the kinetic energy is nothing but the square of the momentum over 2 times the mass. And I'm gonna close this video. This is all I wanted to talk about with about this topic of the relationship between momentum and kinetic energy. Now let's go see the 90 degrees elastic collision special case. Elastic collision special case. So if the situation is the following, so before and after. So before we have a mass m traveling with velocity v1 to the right, and another mass m, so both objects have the same mass, which is stationary, v2 is 0. And afterwards, what's happening is that you have your mass, the first mass moving with velocity v1 prime in this direction given by making an angle theta with the horizontal. And then you have mass 2, sorry, the second mass, which has the same mass, so both objects have the same mass, moving in this direction phi with velocity v2 prime. So if both masses are equal and the collision is elastic, then we get the curious phenomenon that theta plus phi is 90 degrees. Okay, so if both masses are the same and they collide, then they move in 90 degrees. They make an angle of 90 degrees between them after the collision. So let's see the proof, actually. So I'm going to provide the proof. Okay, and I'm going to use vectors, actually. Okay, so this is the momentum before. So P1 is mv1, okay? And as we said, we have to parallel transport the P2's prime vector in this fashion. P2 prime is mv2 prime. This makes an angle phi with the horizontal. And then we parallel transport the first vector, P1 prime, to close this triangle. So P1 is m1 v1 prime. Okay, and this is our angle theta. And we claim that theta plus phi is 90 degrees, which means that this is also 90 degrees. Okay, so since the collision is elastic, then 1/2 m v1 squared, which is the kinetic energy before, is equal to 1/2 m v1 prime squared plus 1/2 m v2 prime squared. So this cancels, and also the masses cancel because they are equal, right? And we find that v1 squared is v1 prime squared plus v2 prime squared. What does this remind you of? This is the Pythagoras theorem, right? So let's bring back the masses. So actually I have some space. So let's multiply with m squared. So m squared v1 squared is equal to m squared v1 prime squared plus m squared v2 prime squared. So I haven't done anything. I just multiplied both sides with m squared because I can cancel this. But what we get is p1 squared is equal to p1 prime squared plus p2 prime squared, which is Pythagoras theorem. Okay, so if we go back to our triangles here, if p2 prime squared plus p1 prime squared, by the way, this is primed, I just noticed. So p1 prime squared plus p2 prime squared is equal to p1 prime squared. So this is the hypotenuse. So this is going to be the hypotenuse of my right triangle. So theta plus phi is 90 degrees because this angle here is 90 degrees. And this is the proof. Okay, and I'm gonna make a short video about impulse next, but I don't want to mix them up here, so I'm gonna stop here.